Welcome, everybody. My name is Victoria. I'm here on behalf of my team, and I'm glad that I'm closing today's session now with the last presentation. I will give you a short overview about our paper in our project, what we do in Germany at the RWTH in Aachen. It's about towards automation in steel construction and extension for the DSTV-NC standard. So let me start by explaining why we actually do this. So automated assembly requires really tight tolerances, and especially steel has really high tolerances in their manufacturing of the base parts. So which actually hinder the integration of robots, because then you always have to manually adapt the program path if the piece is not always the same. So this was one approach that we said, okay, how can we integrate and do the process more dynamic, that we can adapt the path of the robot. And secondly, we are in contact with existing steel manufacturers and companies, and they say, hey, well, our machines already provide internal measurement devices, but we don't use the information for longer term, and we don't store it anywhere. So there's no transparent and ongoing information flow of the data which is actually gathered. So that's why we said, okay, why don't we use an existing format, which is the DSTV-NC, I just explain in a minute, and extend it with some additional information about measurement, about tolerances, but also about the process feedback for further use. So that's why we said, okay, we build upon this DSTV-NC standard because it's widely used in steel construction. And is super clear defined for many steel profiles. So as you can see here, there is an example for an eye profile, but also a round profile. And for every common steel profile, it is defined which is the upper side, which is the lower side, where's the reference point and everything like this. So if you have manufacturing information which goes to the NC machines, everything is linked to this standard. But this standard doesn't have any place to store tolerances or measurement data, and it's not linked to the overall information process, and it's not linked to the machine itself. So that's where we said we take this standard as it is, and it is well clear defined, but we extend it in a way that we have all the information gathered in one central model. And that's why we said, okay, we look into this OWL semantic web language and see how we can integrate this standard into this new data format. And we started by creating, or we used the Ontology Development 101 actually, to set up our domain ontology. And first we had a look if there is already a domain ontology which deals with the automated steel construction, which was not the case as we have found it. So we started by setting up the domain ontology, and we started by asking, or by setting 10 competency questions which should be answered by the ontology. And these questions, for example, were what measurement data actually, what are the measured values I have from the steel part, what is the code which has to be transferred to the machine, but also what is the defined tolerance maybe which I can compare my measured value to. So this was the basis where we started from. And this is a visual representation of our result, basically. So we used the existing IFC OWL structure. So as you can see here, we have an IFC beam, which has an avoiding feature. So we take the example of a drill hole. And this avoiding feature is the drill hole. But from the basis, which you have on the right side, we now extended it with more information on the left side. So you have now defined that this voiding feature is a through hole. It has a diameter, but the diameter is split into different values actually. So you have the planned diameter from the beginning, but you also have then the measured diameter afterwards once you did the quality control process. You have the information where the hole is actually located on the beam, so the X and Y coordinates, and all this information is added to the existing. You only have a hole information. And to validate actually our process, we set it up a workflow in our lab, which starts by having the original plant data of the what you ever want to do with the steel part. For this example, we did some plasma cutting actually of the hexagons. We measured it afterwards, the original part, to see if we need to adapt something. Then we did a really robotic process. We did the measurement again in the end for the quality control, and we add the process feedback to the central model. And everything actually is then stored into the central model, where you can see after each step, the information is actually increased. And we summarized everything in a little video, which we should. So this was a little summary of what we actually did. I skipped this as an example because we had a little quiz. Because what really is interesting, that we can adapt the process while the process was running. So each of these knots were done with a different speed, and everything was stored in a model. And we could react to the result, which was done with a robot, because here the speed was too low and the deviation were too high. So as you can see here, this is an overview of the table. But you can see we integrated every information into the ontology. So you have the existing DSTV data for these 3 cuts. As you saw in the video, we have the 3 hexagon in the beam. We also have the link to the IFC OWL, so which is actually to which voiding feature does the information belong. We have the speed of the machine. We have when it was fabricated. So all the information are now into one single source. And we also have the information about the planned and measured parts of the hexagon and the deviation. So now this is now comes to the conclusion. So we actually are now able to have a base for having an automated C construction, because everything is connected in one source, and the robot actually has also access to this model and is controlled by the model, and we can then use the information to adapt to it. the best thing is that we have now a link from the planning data to the actual manufacturing data, and everything is stored for longer term. So you can also use it later if you want. If you think of reusing the steel beam, then you have the information. Hey, when was it transferred? When was it manufactured? What is the deviation from the plant, and so on. So which is then used for for future use. Yeah, and. Further, in the future, we will look into other processes. So far, we have looked at the holds, but also the plasma cutting, because for every construction or steel process, you have to see what information is really necessary for the future to put into this model. And yeah, this is so far, but our approach is feasible, and thank you very much.